Welcome to Mrs. Z's Chemistry. In this video, we will learn how to calculate the pH when we mix an acid and a base together. These are called neutralization reactions because the acid and the base neutralize each other, and when they react, they create a salt and water. Remember that in chemistry, a salt is any ionic compound. Sodium chloride is what we call table salt, but any ionic compound, for example, sodium fluoride or potassium chloride, potassium fluoride, lithium chloride, any of those are called salts. So in this reaction, this is a general reaction where the A is representing the anion that is in the acid with the hydrogen ion, and then the B is representing any cation that's with hydroxide that's making the base. When they react together, the A and the B form the salt, the cation and the anion, and then the hydroxide and the hydrogen ion create water. So let's try this problem. We're going to calculate the pH when 20 milliliters of a 1 molarity HCl solution is mixed with 18 milliliters of 1 molarity sodium hydroxide. This is the chemical reaction that is being formed here. The HCl reacts with sodium hydroxide to form water and sodium chloride. These react in a 1-to-1 mole ratio, so we need to find the moles of each of the compounds first. We can find moles by using the volume and the molarity of each of the solutions. The molarity equation is moles over liters. So if we multiply molarity times liters, we can get moles. So we have 20 milliliters and a 1 molarity for HCl. Let's turn our volumes, milliliters, into liters. There are 1,000 milliliters in 1 liter. So this leaves us with 0.0200 liters. And then also we've got 1 molarity of HCl. So when we multiply these together, we're going to get 0.02 moles of the hydrogen ion. HCl is a strong acid, so it will completely dissociate in solution. And the hydrogen ion is what we need to use in order to calculate pH. So we don't really care about the chloride ion in the solution. Then we do the same thing with the sodium hydroxide solution. We've got 1 molarity and it's 18 milliliters. So turn your 18 milliliters into 0.018 liters and we're left with 0.0180 moles of hydroxide. Again, sodium hydroxide is similar to the HCl in that it is a strong base. It will completely dissociate, and all we are worried about is the hydroxide and the hydrogen ions. Those are going to react, and we want to see how much we have left over. So a great way to visualize this is using a before, change, after chart. We're not going to include the water or the sodium chloride because it doesn't matter how much is produced of either of those. We're wanting to know how much hydrogen ions and how many hydroxide ions are left over. So here's before the reaction. You have a beaker of each of these solutions. In the acid beaker, you've got 0.02 moles, and in the hydroxide or base beaker, we've got 0.018 moles. We can see that the hydroxide is the limiting reactant. When we use up that much and react 0.018, we end up with 0 hydroxide. And then when you subtract that from the amount of the hydrogen ions, we are left with 0.00200 moles of hydrogen ions left over. So in order to find pH, we need to take the negative log of the molarity of hydrogen ions. Moles and molarity are two different things. Remember that molarity is moles divided by liters. So here's the moles of hydrogen ions that's left over. All the rest of the acid reacted and turned into water and salt. So we can't count that towards the pH. Our total volume now, imagine we had a 20 milliliter beaker and an 18 milliliter beaker and we mixed them together. We now have a total of 38 milliliters of solution. And the 0.002 moles of hydrogen ions are in that solution. So the concentration is those moles divided by the total volume. We just got to turn our 38 milliliters into liters. So here's the molarity equation, 0.002 moles of hydrogen ions divided by 0.0380 liters, that's our 38 milliliters, This leaves us with 0.0526 molarity or concentration of hydrogen ions. Take the negative log of that to find the pH. This pH makes sense. We always need to make sure we do a reasonable check. And this makes sense because we know we have hydrogen ions left over in the solution, therefore it should be an acidic solution. 1.279 is an acidic solution. Anything less than 7 would be reasonable for this problem. So go ahead and try this next problem. Calculate the pH when 50 milliliters of 0.48 molarity HCl is mixed with 60 milliliters of 0.45 molarity sodium hydroxide. Pause to see if you can work this problem out. In the first step, we need to find the moles of each solution. So if we color coordinate some of this here, we've got 50 milliliters of 0.48 molarity hydrochloric acid. That's right here. Make sure you turn your 50 milliliters into 0.05 liters. When you multiply that together, you've got 0.0240 moles of hydrogen ions. We'll look at the base in blue here. We've got 60 milliliters of 0.45 molarity sodium hydroxide. That's right here, molarity times liters. And we're left with 0.0270 moles of hydroxide. Just looking at these two numbers, we can see that the hydrogen ions are going to run out first when they start reacting because they react in a 1-to-1 ratio. And the hydroxide ions are going to we're going to have some hydroxide ions left over. You don't have to write out the BCA or before change after chart, but it's a good visualization. Really, all you need to do is subtract the two and realize that we have 0.003 moles of hydroxide left over. From there, we need to find the molarity. So we have a total volume of 110 milliliters because we mixed 50 milliliter with 60 milliliters. So we have moles of hydroxide left over divided by total volume turned into liters. This leaves us with 0.0273 molarity hydroxide. When we take the negative log of that, that gets us POH. And then use your simple equation to connect pH and POH. 14 minus POH gets us pH, which is 12.436. Now, does this make sense for this situation? Well, yes, it does, because we know that hydroxide was left over in the solution and all of our hydrogen got reacted. So this should be a basic solution. Anything above 7 is a basic solution. Above 7 pH is a basic solution. So yes, 12.436 does make sense for this solution.